2020. He did his PhD at IMPA, advised by Fernando Codá, in March 2014. He was a postdoc at Imperial College of London at University of Warwick. He was an IAS fellow at Princeton in 2018 to 2019, and Warwick Zeeman lecturer in 2019 to 2020. His research is in geometric analysis in general and on the geometry of minimal submanifolds in particular. Today he will talk about systoles and diastoles of low-dimensional sphere. So on behalf of the organizers, I want to thank you for honoring us with your presence, and thank you very much. I'll give you the word.
Okay. So thank you very much, Tarcísio, for the invitation, for the reception. It's a great pleasure for me to be here at the Universidade de Brasília. It's not my first time. When I was a student, I participated at the School of Geometry here. But I'm very happy to be back. And actually, this is, well, since March 2020, my first face-to-face congress that I'm participating in. So it's I'm very happy with this occasion. Okay, so this is the title of my talk. I think nobody needs to worry about the title. This is not a talk about medical issues. However, I think it's nice to begin with the medical meaning of those two strange words, systole and diastole. So, as you all know, the heart beats periodically, and the doctors distinguish between two moments of this movement. The moment of contraction and the moment of expansion. So the moment of contraction is called the systole, and the moment of expansion is called the diastole. Okay? And how this terminology entered in geometry? So it was an idea of Marcel Berger, a great geometer of the 20th century, to describe a certain geometric invariant that he was interested about as the systole of the shape. So here we see a shape that is like a torus, and then we see lots of curves that are closed curves, and they go into the hole of the torus. And the idea is that because they go into the hole of the torus, they cannot be continuously deformed until a point. Okay, they get stuck into the hole. And so the thing that Berger called the systole is the least length of such loops that cannot be shrunk to a point. So maybe in this picture, you could think this red curve here has length very close to the actual value of the systole. Okay, so this is a definition that works whenever your manifold has non-contractible loops. However, how about the simplest shape that we can think of? How about spheres, right? And in spheres, we all know that the sphere is simply connected, so every closed curve can be shrunk to a point. How can we make sense of a systole in this case? And also, keeping up with the idea of the analogy, what is the thing that we should call the diastole? Okay, so this is going to be the motivation of this first part of the talk. Okay, so let's start in two dimensions. So I will talk from now on about topological spheres with a Riemannian metric, which, if you have never seen this, is just a way to measure lengths of tangent vectors and angles between tangent vectors. And with this structure, you can do geometry as we like. We can compute lengths of curves, we can compute areas of regions, we can compute curvature, and everything else. So here on the left, I made the picture of the Euclidean sphere of radius 1, and the induced metric is the one that we will call the canonical metric of the sphere, the round, most symmetric one. Here we have another sphere with a different metric, which makes it like an oval. And finally, we have a very strange geometry. I don't know, but this is still a two-dimensional sphere. Okay, so in order to define the systole of a sphere with a Riemannian metric, I need to talk about periodic geodesics. And geodesics, as you know, belong to two different realms. The realm of dynamical systems and the realm of geometry. So let's have a look first at the dynamical definition. So what is a periodic geodesic? It's just a periodic map from the line to the sphere, a non-constant periodic map whose acceleration is identically 0. Okay? And why is this the dynamical definition of the geodesics? Because behind this equation here, if you write it in coordinates, you see a second order homogeneous ODE. And this has a consequence, right? So if you think of the existence theorem for ODEs, it will tell you, for example, let's have a look at this picture here. If I give you a point in the sphere, and if I give you a tangent direction at that point, then I can solve the ODE for geodesics and find, at least close to that point, a geodesic that goes exactly through that point with that given velocity vector. Okay, and so here I try to draw what the geodesic would look like. Okay, so given a point in the direction, you can shoot the geodesic. But I'm interested in periodic geodesics, so we need to know conditions that guarantee that, I don't know, I travel a bit and then I go back to the same point with the same tangent direction. In the case of the canonical metric, it's a very standard exercise. We ask, everyone who gives the course on differential geometry asks this question for their students, which is to compute the geodesics of the sphere. And the geodesics of the spheres are, which I will call in this talk, the equators. So the great circles, the circles that you see when you intersect the Euclidean sphere with a plane that goes through the center of the sphere. Okay, so like this green equator here. Very well. So when we have a look at this last picture here, then it's not very clear. Well, even this ovalloid picture here, it's not very clear if there are periodic geodesics at all or not. Right. So this is a question that we will need to worry about soon. But before that, let me give you the geometric definition. And so what is a periodic geodesic? I'm going to consider it as a map from the circle to S2, that is an immersion, and has this funny property here. So think of this blue curve as gamma 0. So this is a curve that belongs to a one-parameter family of curves, gamma t. So gamma t is varying the curve gamma 0. And what I'm going to do, I'm going to compute the length of all those curves, gamma t, and then I will differentiate this length at time t equals 0. Okay? So the curve gamma 0 is going to be a geodesic whenever I get 0 as the value of this derivative for every possible variation of gamma 0. Okay, so you have to imagine always to vary gamma 0, and gamma 0 is a geodesic when this derivative is 0 for all such variations. Okay, so this is why I call this a geometric definition, and actually it's a geometric variational definition, because I have the functional, the length assigns to each immersion of the circle a number, and I'm looking at exactly the critical points of this function. Okay, so let's go back to that problem that I stated, which is, can we find at all a periodic geodesic on any Riemannian two-sphere? Well, the first one to propose this question was Poincaré in the beginning of the 19th century. And of course, Poincaré was a dynamical system guy, so he was really worried about the dynamic of the solar system. But he started to realize that it was very important to look at the periodic orbits of the dynamical systems. And then he thought about studying periodic geodesics as a simpler case of the general question that he was thinking about. And he gave an argument that works when your sphere has positive curvature. Okay, so like a ellipsoid or an oval shape. And a few years later, Birkhoff gave the final answer to the question. So he showed that for every Riemannian metric on S2, you do find at least one periodic geodesic. Okay, so very striking existence theorem. Now, once we know that there is at least one periodic geodesic, it makes sense to ask what is the least possible length of such object. And this is actually the definition of the systole of a two-dimensional Riemannian sphere. Okay, so the least length of a periodic geodesic for this metric. Well, by Birkhoff's theorem, there is at least one, so the number is finite. And it's a very easy argument to show that the length cannot be arbitrarily small, because if the length is too small, the points in the geodesic are too close to each other, they lie in a convex neighborhood, and so they cannot be a geodesic. Okay, so this is the systole of Riemannian two-sphere, and now that we have this number, the interesting question is, well, what kind of geometric feature of the sphere is it capturing, right? So what kind of geometric information does it contain? And the right way to answer this kind of question is to compare your invariant, the systole in the case, with other invariants, like, I don't know, the curvature, the diameter. You can make your choice. And in this talk, I will be particularly interested in the comparison between the systole and the area. And notice that those are two global properties of S2, right? Not, I'm making here the contrast with the curvature. Curvature is a local notion, something that you compute knowing only the behavior of the geometry around a point. But here, I need to know the geometry of the entire S2 in order to compute the two invariants here. Okay. Okay, so it's always good to begin with a simple family of examples, right? So, and here I want to show you what happens when you try to compute the systole compared to the area in the family of ellipsoids. Okay, so I'm writing this quotient here, systole divided by the square root of the area, because this quotient here is invariant by scaling, right? The systole scales like length, the area like area, so if I multiply the metric by c, the length will be multiplied by square root of c, and the area by c, so this is the right way to forget about the scale and do the comparison in an elegant way. Okay, so I'm considering here the ellipsoid, where I deform one of the horizontal principal axis. And here I drew a picture. So the red one is the round metric, the standard Euclidean sphere. The red one with a smaller a, I guess, and the blue one with a bigger a. And why, I mean, the ellipsoids are particularly simple to understand because it's very easy to check that the coordinate planes intersected with the ellipsoids, they are periodic geodesics. So you have for free three geodesics whose length you can use to estimate the systole from above. Right? The systole is the smallest possible length. You have three geodesics. The length of each one of them will give you an upper bound. And so it's very easy to check, for example, that when A goes to, I wrote 0, but I think should be infinity, right? Yeah, because I want to make the axis longer and longer so that the area will increase as much as I want, but the systole will stay bounded because there is always this geodesic here, the one appearing when you intersect the ellipsoid with the YZ plane. So this one is a geodesic for all of them. You don't change the length. And so this number is bounded by a constant. So the numerator is bounded by a constant, the denominator goes to infinity. So as I do this deformation, I get 0. Okay, so this number, this quotient, can be as small as we wish. And how about the opposite direction? Can it be arbitrarily big? And then something interesting is happening. Because if you try to, say, pass from the canonical metric, the red one, to the green one, you shrink the size of one of the axes. Okay, so both still have this red vertical geodesic here, but the green one has this other one, the one that appears as I intersect the ellipsoid with the xy axis. And this green one has less length than the red one. So two things happened as I did this deformation. So the systole has decreased, but also the area has decreased, right? So it's not very clear what happens to the quotient. Right? But still, you can do the computation explicitly and check that this number here for every a is bounded from above by the value that you get for a equals 1, so the value that you get for the Euclidean sphere. And the value that you get for the Euclidean sphere, so the sphere of radius 1, the great circle has length 2 pi, the area is 4 pi, so the computation gives you the square root of pi. Okay? So the lesson from this example is that, well, the systolic quotient here, systole divided by square root of area, can be arbitrarily small, but it cannot be arbitrarily big. Okay, so then Kroc in the 80s came with this amazing theorem, which tells us that what we observed in the case of the ellipsoids is actually true for all Riemannian metrics. So what he proves that if you fix the area of your Riemannian two-sphere, there is an explicit universal constant C that is an upper bound for the systole of this metric. Okay, so if you fix the area, you know for sure that you will be able to find at least one periodic geodesic whose length is at most this universal constant. That doesn't depend on the metric at all. Okay? And okay, so this is amazing result. And I can state for you an open problem about this constant. I mean, until today, nobody knows what is the sharp constant. So after Kroc, many people worked on the problem. I think the best available result is this one by Regina Hotman. And she got the constant C equals 4 times square root of 2. But this is still a bit far from the number that Kroc conjectured to be the sharp number. So square root of 2, this number here is the one that Kroc thinks is the right number. And notice that this number is bigger than square root of pi, which is the systolic quotient of the sphere with the canonical metric. So this is an interesting feature about this problem. So this is a maximization problem, if you want, where the round matrix is not the shape that optimizes the problem. Okay, and so okay, so this is a, I mean, this thing is red. This thing in red here is true. People know how to prove this, and the conjecture is actually that C equals square root of 2 square root of 3. Okay. So now I want to tell you a bit about the work of Birkhoff and give you an idea about how he got the existence of a geodesic, of a periodic geodesic for all Riemannian two spheres. And the idea is very intuitive in a way. So think of you are given your Riemannian two sphere, and you also have a piece of, I don't know, a string that you make a knot to make it a closed string. And this closed string has a length, L. Now you ask the following question. How big must L be so that the sphere goes through the loop? Okay? So if the loop has an enormous length, then of course you can make your sphere to pass through the loop. If the loop is too short, then if you try to pass the sphere through the loop, it will get stuck, right? And so there is a transition between the behavior. It passes, it doesn't pass. And this number L in the intuition of Birkhoff should be the length of a periodic geodesic. So let me go into more details. So let's try to model mathematically this idea of a closed loop going through your two-dimensional sphere. Okay? And how can we model this? Well, I think it's very natural to consider this this kind of object here. So we think of the Euclidean sphere. The Euclidean sphere is, of course, foliated by horizontal circles. And then, given our arbitrary Riemannian two-sphere, we can consider maps from the Euclidean sphere to this arbitrary sphere, which are continuous maps, which send each one of the horizontal circles on this side to I don't know, a piecewise curve in your S2G, and then to capture some non-triviality, some idea that, I mean, the lace is really going and covering all the two-sphere and not going up to a certain point and then going back, I will ask this map to have degree 1. Okay? And then what Birkhoff did was to define this number, which is, so for each such f, for each such family of curves sweeping out S2, you will compute the maximum length of the curves in the family. Okay, so you have the green curves here. You will try to find the one that has the maximum length for this family F, and then you will minimize over all possible Fs. Okay, and well, in the last talk we saw a bit about the Monton-Paz lemma. This is similar because we are going through, well, -1 is sent by F at a point, a curve with length 0, and 0 is the absolute minimum of the length functional. And then we end at the point curve again, which has length 0. And what we are trying to do is to go from the absolute minimum of the length to the absolute minimum of the length while passing through the whole two-sphere. Okay, and what's the final result? What Birkhoff actually proved was that this number is positive and that it is realized as the length of a periodic geodesic. Okay? By the way, to see that this number is positive, there is a very nice geometric argument, which is the following. So notice that as we go from -1 to 1 here, say if we keep track of what is below each one of those circles, the beginning is different from the end. Because at the beginning, there is very little area below the circle. But at the end, the whole thing is below the curve. So, and here that happens also in the image of F, right? So this family of curves sweeping out S2 with the metric G, so this family gamma T, there will be some time T where this curve gamma T will divide the sphere in two pieces with the same area. Okay? And then you recall the isoperimetric problem. What's the isoperimetric problem? Well, you want to ask what is the least amount of length that you need in order to divide your shape into two pieces of the same area. And so this isoperimetric number is a positive lower bound for WB. And this was all that was needed. Well, and I mean, a lot of several technical work, a lot of serious work, but I mean, this idea that, think of the Monton-Paz, right? So we are going from 0 to 0, but what I'm telling you is that there is a definite amount of functional that you need to go up along this path. And so the idea is that as you minimize over all paths, you will find a critical point, which is the periodic geodesic that Birkhoff found. Okay, so yeah, and well, since Birkhoff showed that this number WB is realized as the length of some periodic geodesic by the definition of the systole, we know that this number here is upper bound for the systole. Okay. And this is interesting to be remarked about because I mean, if you start to think about, okay, the systole is the least length, but how exactly can you estimate this number? But how can you estimate this number if you don't know? I mean, if you don't know the geodesics of the space. So what this theorem of Birkhoff not only gives you the existence of the geodesic, but it also gives you a way to estimate the length of the geodesic it produces. Because if you take any such family and compute the maximum length, then you get an upper bound for WB, and therefore an upper bound for the systole. So the better estimate, the better you can sweep out the two sphere in terms of keeping the length small along the family, along the sweep out, the better estimate you will have for the systole. Okay, so let's have a look now at the example of the three-legged starfish, right? So the starfish usually has 5 legs, but I'm not sure if there is an actual three-legged starfish in nature. But I mean, we can make this picture. And so let's try to follow intuitively that idea of Birkhoff of taking the loop and trying to make the shape pass through the loop. Okay, so this leg here is somehow thin, so you don't need much length of your loop to make it go through this piece of leg. However, to go to the other side, you will need to go you need to go up, and you need to have a lot of length so that you can pass through this vertical leg here, right? And then you can go down again. So what this example is showing is that somehow, I mean, the invariant of Birkhoff WB should be big in this case, right? You need your loop to have a lot of length so that it can really pass through all the legs. And now let's try to modify this picture a bit. So let's try to make the legs thinner. So when you do this, the total area will decrease, right? So if the legs are thinner, the area will decrease. But then you can increase the size of the legs, make them longer, so to compensate and find a new three-legged starfish with the same area as before, but with longer and thinner legs. Well, okay, so remember the area is kept fixed, but how about the WB invariant? How about the length of the geodesic that Birkhoff finds? It will also increase, right? Because the leg became longer as well. And so this seems to be a bit tricky, right? When you think about the theorem of Kroc. Because Kroc said, okay, if you keep the area fixed, there is this universal constant that's a bound for the systole. What I'm telling you here is that this number doesn't have this property. So WB can be arbitrarily big, even though you keep the length, the area of the sphere the same. And so, well, where is the geodesic that Kroc found? And I claim that is this one here. This one that is not a simple geodesic. It has a self-intersection, but it crosses, I mean, the two legs, making a 8-figure shape. And so you might wonder, okay, can I find this geodesic still by a method similar to Birkhoff's method? And the answer is yes. So the idea is now that we have to allow more general ways to sweep out our two-dimensional sphere. So before we were sweeping out our two-dimensional sphere by loops. But maybe it's a better idea would be to sweep out the sphere by the boundary of regions, like those regions omega t that I drew here. So think of this omega t going up, like vertically here, and then I will measure the length of the boundary of those regions. Okay? And this suggests the definition of what I want to call the diastole. So for every such family of regions sweeping out the two-dimensional sphere, I will compute the maximum length of the boundary of these regions, and then I will minimize over all possible regions. Now, I realized I made a small mistake here, because the right thing should be the boundary of omega 0 is 0, and the boundary of omega 1 is 0, so that the beginning of the deformation have the empty curve, the end of the deformation also have the empty curve. But then I need also to keep track of this idea of the regions sweeping out the sphere. They need to pass through all regions of the sphere. And the way to do this is to impose the condition that omega 0 is the empty set, and omega 1 is the full sphere, right? I mean, the empty set, the boundary of the empty set is 0, is empty. The boundary of the true sphere is also empty. So it's still a family that starts at nothing, ends at nothing, but the beginning is different from the end. Okay. Okay. So and this is my proposed definition of diastole, and I hope you can see somehow this number is capturing this idea of an expansion, in contrast with the systole. Okay, so Almgren-Pitts and Calabi-Crook. So Almgren-Pitts working full generality and Calabi-Crook working in 2 dimensions for the sphere. They showed that this number here that I defined like this is also the length of a periodic geodesic. And so again, this number here gives an upper bound for the systole. Right? So the systole is less than the diastole. They can be equal, actually. It's not a good thing if you are, I mean, we are talking about the human heart, because I think, well, the heart will be stationary. It's not a good position to be. But, I mean, there are shapes where, I think actually this shape here, the diastole coincides with the systole. Okay, so maybe this is the summary of the story. Here should be the shortest geodesic, maybe going through this neck, and then these are the geodesic that appears by Birkhoff or the other min-max procedure. Okay. So it's always very tricky to figure out what is the diastole when you look at the picture, right? Because think of the definition, right? So we have to analyze all families sweeping out the sphere and then maximize the length and then minimize overall families. So, okay, so there is an obvious family where such geodesic here is the slice of maximum length. But maybe there is a very strange one, a different one, sweep out, which would win compared to this one. But anyway, I think this is a reasonable picture of what we are observing. Okay, so maybe. Okay, no problem. Okay, so this ends the discussion about the true sphere, and now I want to go to higher dimensions. Okay, and then we have to think about what we want to do, right? Because we can go from the true sphere to the tree sphere and keep talking about geodesics. It would be a choice, but I want to also increase the dimension of the object that I'm considering. I want to go from a curve to a surface. And the right analogous of periodic geodesics, I think, should be minimal spheres. Why is that? I mean, when you go to higher dimensions, this ODE principle, you lose that, right? So your objects are not anymore described by ODEs. So you need to maybe rely on the geometric definition and make the analogous definition, which is, so instead of talking about critical points of the length functional, you talk about the critical points of the area functional. And the critical points of the area functional are known as minimal submanifolds. And so this is my choice. So instead of talking about periodic geodesics in a Riemannian two-sphere, I will talk about minimal two-dimensional spheres in a Riemannian three-dimensional sphere. In the 80s, Simon and Smith developed a min-max theory, which is an entire analogous of the Birkhoff theory. And, well, in this theory, they defined this number, a very similar min-max number. We sweep out S3 by two-dimensional spheres in a similar way to the one that I defined. And they proved that this number here is realized as the area of a minimal two-sphere. I mean, not quite as I said, because in higher dimensions you need to take into account multiplicities and maybe connected components. So the idea is that now this number here is attained as the area of a bunch of disjoint embedded minimal two spheres, and the area of each one of those two spheres is counted with an integer multiplicity. But still, if this number is realized by such collection of areas of spheres, then it of course gives you an upper bound for the least possible area of an embedded minimal two sphere in S3. Okay? And so that's it. So Simon-Smith theory gives you the existence of an embedded minimal two sphere for every Riemannian three sphere, and moreover, it gives you a way to estimate the area of this minimal two sphere. So this number is the one that I will call the spherical diastole in this talk. It's not a standard terminology, but let's keep the analogy. And the least area I will call the systole. Okay, so keeping the analogy with the previous case. And now let me show you a few theorems that I proved about the comparison between this number here, the spherical diastole, and the volume of the Riemannian three sphere. So the first results are part of a joint work with Rafael Montezuma from the Federal University of Ceará. And then let me go through three statements here. So the first one is that we checked that that theorem of Kroc is false in this context. Okay, we found sequences of Riemannian matrix on S3, all with the same volume, but such that this spherical diastole is arbitrarily large. Okay, and these the examples that we were able to compute were actually homogeneous matrix with positive Ricci curvature. Actually, maybe some of you may know the Berger spheres, and this is the family that we analyzed. So the Berger spheres, so the sphere, you can see, the three-dimensional sphere you can see as lying inside C2 pairs of complex numbers with norm, well, the sum of the two norms is equal to 1. And in C2 you have, of course, the multiplication by unit complex number on both coordinates. And this generates a S1 action on your S3. So the Berger spheres appear when you change the size of those circles, those orbits of this action. Okay? And so it's a very simple, very concrete family of metrics, and we were able to compute that this supremum here is plus infinity. Okay? Okay, so yeah, maybe you are thinking about the star leg, the three-legged starfish but the three-legged starfish doesn't have positive Ricci curvature. In 2 dimensions, so this is actually a theorem by Calabi and Cow. In 2 dimensions, when the curvature is positive, the systole coincides with the diastole. So that theorem of Kroc, I mean, would cover this case as well. So this result here is really in contrast with the theorem of Kroc. It shows that in 3 dimensions, a new phenomenon is appearing. Okay, so let me go through the second statement, which is the following. So since we know that, I mean, there is no absolute maximum for this quotient here in the space of all metrics, it makes sense to restrict your metrics to an interesting family. And the family that by certain analogies, we consider the family of metrics that are conformally flat. So you take the canonical metric and you take a positive function, multiplying the canonical metric, so this gives you a conformally flat metric. Okay, so let's consider conformally flat metrics with positive Ricci curvature. Then we were able to show that the spherical diastole, WSS, is bounded from above by this number, cubic root of 16 over pi, times the volume to the right power 2 over 3. Okay, so I forgot to keep 2 over 3. I want an inequality that is scaling invariant, right? And so there is an upper bound in this open set in the space of conformally flat metrics. And moreover, the equality case can be characterized. So if equality holds, then you must be isometric to the canonical sphere with constant sectional curvature. Okay, you must be round. And so again, there is a contrast here with the 2-dimensional case, because in 2 dimensions, there is the uniformization theorem that tells you that any Riemannian metric on the 2 sphere is conformal to the canonical metric. And remember, I said in 2 dimensions, the round metric is not the maximum among conformally flat metrics. The constant of Kroc conjecture is strictly bigger than the constant that you see for the sphere. Right? So again, there is something new happening in, it's a bit surprising, right? So in 3 dimensions, we got a cleaner result than what is known in 2 dimensions. But still, this is the result. Okay, and then the last result that I want to mention has a very weird statement, but the idea is the following. So, okay, so by theorem 2, the result 2 here, we know for sure that there is at least one metric with positive Ricci curvature, namely the canonical metric, which is a local maximum of the quotient WSS by the volume to this power, that is a local maximum of this functional in that conformal class. Okay? And this local maximum is attained uniquely by the constant curvature metrics. So if you try to draw the picture of the functional, you could imagine some sort of parabola, I don't know, pointing downstairs with a unique maximum. And so if you heuristically, right, so if you perturb this a bit, so if you perturb the conformal class a bit, you should expect to see also this behavior. So you should expect to see in different conformal classes also a local maximum of the normalized spherical diastole. And so we asked ourselves, what is really special about those locally maximizing metrics? So can we say anything interesting about them? Should they look like the round sphere, or I mean, what is really the Euler-Lagrange equation of this maximizing metric for this function? And one of the properties that we deduced was the following. So let's start from the beginning. So if you have a Riemannian metric 1s3 with positive Ricci curvature that maximizes this functional here, in the conformal class it defines then you can find a sequence, sigma I, of embedded minimal spheres, all of them with the same area equals to WSS, and such that they are equidistributed in space. So this is what this formula means. They are equidistributed in space. So if you want to compute the average of a function on the whole three-dimensional sphere, this is the same as computing the average of this function on each one of those embedded minimal spheres of the sequence. You compute the average on each of the spheres. Then you compute the average of the first k numbers that you get, and then you compute the limit as k goes to infinity. And why do I say that this is an equidistribution property? Well, because let's assume, for example, let's try to show, for example, that sigma i's, those sigma i's in the sequence, they need to intersect, I mean, at least one of them needs to intersect any arbitrary open set that you choose. Okay, so let me try to argue this. So let's assume not. So let's assume there is an open set U, and let's assume that none of those sigma i's go through that open set. Okay, so in this open set, I can find a bump function, a cutoff function, positive inside U and 0 elsewhere, which will give me a positive number in this left-hand side here, right? On the other hand, since I'm assuming that none of the sigma i's goes through the support of this function, the average will be 0 for every I. And so on the right-hand side, we will be getting 0, and this is a contradiction. Okay? So this is the key idea. So a local maximum basically should have embedded minimal spheres realizing the diastole passing everywhere somehow. And if you think about the sphere, it has this property, right? So because you have the equators, and you have equators passing through every open set. And more than that, actually, in the case of the round sphere, the canonical metric, the equators not only pass through every point, but also through every point and every given two-dimensional tangent plane at that point. So they are actually passing through all points in the Riemannian of two planes. And so after I finished this work with Rafael, I had this observation pretty much in mind. And I mean, if you want to really make a study of this functional, maybe the good candidates to be maximizing metrics should be those Riemannian metrics where through each point and through each two-dimensional plane, you can find a two-dimensional sphere whose area is equal to the diastole. Okay? And this was my motivation. My other collaborators, Fernando Marques, Fernando Codá from Princeton, and André Neves from Chicago, had different motivations, and then we got together, and we did this work. My most recent work, which is, the aim of the work was to construct examples of Riemannian n-dimensional spheres containing families of embedded minimal hyperspheres, codimension 1 spheres, that are all minimal with respect to that metric, and I want also this family to have this property. For every given hyperplane in the tangent space, I can find exactly one element of the family which passes through that point with that given tangent plane. Okay, and as I said, these are good candidates to be maxima of the diastole compared to the volume. Okay, so we learned one thing afterwards. I know now for sure that some of the examples that we construct here cannot be local maxima. Okay, so it's not an if and only if. However, I still think it's worth to study those metrics here in relation to the problem of maximizing this function, because I think they are still very good candidates to be maximizing metrics. Okay. Okay, I think this is more or less the end of the story. I can tell you a few things more. I don't know how much time do I have. Maybe now I'm over time. 5 minutes. So maybe you have some curiosity, and I will leave you to ask the questions according to your curiosity. Okay, so thank you very much for your attention.
Thank you very much, Professor Ambrozio. Any questions, comments?
Okay.
How about minimal spheres inside other type of manifolds, like the torus, higher dimension?
Yeah, so if I want to keep talking about the systole and the diastole as a way to distinguish certain special minimal surfaces in an arbitrary three-manifold, say, then I need to allow other topologies. I need to allow, instead of doing sweep-outs by spheres, I need to do sweep-outs by more general surfaces. And so this gives the right number to be analyzed in comparison to the volume. So the point I'm trying to make is that maybe okay, so you can compute, maybe for certain metrics, the least area minimal to sphere. But this is too big compared to the volume. The one that is good for comparison with the volume, it has another topology. So this is why I don't usually think in these terms. I don't change the ambient topology and keep thinking about spheres. Instead, I change the topology, and then I do this more general min-max and try to compare the new min-max number, which is realized maybe by a different topology of a soft surface, and then compare it to the volume. Okay? So I can give a concrete example. So I mentioned even keeping the three sphere. So in the family of Berger spheres, if you start decreasing the size of the fiber, then you see the following. So the least area minimal surface will be a sphere until a certain time, and then it will become, so the Clifford torus, for small enough length of the fiber, it becomes the least area minimal surface that exists in the Berger sphere. And this one is the one that is good for the comparison with the volume. The sphere is not. The sphere we showed, the comparison with the volume makes it go to infinity. But if you think of more general minimal surfaces, then maybe you have a better control.
Any other questions? So let's thanks again.
Thank you.
Muito obrigado, Lucas.
Thank you all. And we meet again here tomorrow for the other plenaries at 9 o'clock? No, at 10, huh? 10 o'clock. For the other plenaries, and the activities on the afternoon are now on the main campus near the math department.